Hello, thank you for joining us. Welcome to this webinar event. This is one of many such webinar-based professional development events brought to you by Texas Instruments Australia as part of our ongoing support for teachers in the classroom. Today's topic, enhancing student performance in the further mathematics modules. Your presenters this evening, Craig Brown and Sanjeev Meston. My name is Brian Lannon. I'm your host for this event, and I'm also the technician and am recording this event, which you may watch again at a later stage. First panellist this evening will be Craig Brown. Good evening, Craig.
Good evening, everybody.
And Craig comes to us from St Ignatius College in Geelong. He's been teaching for a couple of 2.5 decades, all levels of mathematics, of all the senior mathematics, and the thing I always like to see here, been active in offering PD to teachers in the schools that he's taught, as well as in other schools. Thank you very much for your input this evening, Craig.
It is a pleasure, Brian.
As always. Our other presenter this evening, Sanjeev Meston. Sanjeev is Head of Teaching and Learning and Curriculum at Lakeside College, also a TCube National Instructor, has presented at our international conferences, teaching maths and physics over a few decades there. Good evening, Sanjeev.
Hi, Brian, and hi, everyone.
And so we look forward to hearing from both these gentlemen. In fact, I know some of the material that Sanjeev has in store for us this evening. I did see him present that quite expertly at the International Conference in San Antonio earlier this year. So some good ideas on the way there.
And good evening, everybody. Look, so this first page here, I've just got a little bit of a snapshot of what we're going to cover tonight. First of all, we will look at drawing some graphs and finding some key features and having a little play with the sliders. After that, we'll look at some basic calculator skills, solving simultaneous equations, both graphically and also using the solve function, finding equations in straight lines. I've got some notes pages that will help us basically make answering these questions quite efficiently. From there, we're going to be looking at graphing regions defined by inequalities, and finish lastly with looking at nonlinear relationships as per the study design for further maths in this module. But before we get on with that, though, I've got written in red here something that we perhaps need to be looking at is the settings on the graphs page, because sometimes the default setting is actually float 3, and that is often not perhaps displayed to enough decimal places that we need. So I'm just going to show people that. So what I'm going to do is click onto my next page here. Now, if we're going to open up a graphs page, we would often, the default setting is the function mode, if you like, of the calculator. Now, if I press menu, now if we go down to settings down the bottom here, we will notice that, in fact, this is where we can, in fact, change the float display on our graphs page. Now, for memory, I think it's float 3 is the actual default setting, but you can naturally enough change it to whatever float setting we'd like. But you'll also know there's also the auto option. The auto option matches the general settings that you would set for the document, so that's actually worthwhile knowing as well. So if you're finding that on the graphs page that you are, in fact, looking for a certain number of decimal places or something like that and not getting enough, then I would check this setting on the calculator. I'm going to keep mine on auto for now. I'm going to make default and continue on. Now, at the moment, we've got the function mode of the calculator, but what I'm going to do is actually not present the graphical information using this. as you can see, I've got the cursor beside F1 of X equals. If I press Control Menu, and then hit number 1, which is Graph Entry Edit, I've in fact got a number of options of different graphs that I can plot. What I am going to use is the relation setting instead, which now changes to rel1 x, y. When it's in this mode, I can actually type in y equals 2x plus 1, or 2x plus 2, for instance, and press enter and get our graph up and running nicely. But not only that, if I in fact hit tab and possibly draw another graph, I can type in 2x plus 3y equals 6. And so it'll take all the different forms of a linear equation quite nicely, as you can see. If I hit tab, I can in fact type in x equals 3 to get my vertical line, and I'll hit one more just to get the complete set. If I hit tab, we can type in y equals 2. And as you can see, I've got all sorts of lines there, and it's just a nice way of being able to present our linear graphs. Now, what we can also do is, in fact, explore graphs by using sliders. And so what I've done here is created the model y equals mx plus c. And I've got two sliders here, M and C. M here, if I click on that, we can see that in fact that's changing the gradient accordingly. And if I click on C down here, you'll notice that in fact that is moving the value of C. Perhaps I should in fact move that across 1. Now I'll use C. As you can see, it's changing C. Now, people might be wondering that in fact the two sliders I've used here in fact look quite differently. This one here that I've actually got C, that's actually minimized. We can actually change the settings of these sliders. The obvious thing to do that we might want to do is actually change the minimum and maximum values here. So if I change this to -2, for instance, and change this to 2, that's a nice easy change to make. But if I highlight the slider and press Control Menu, this is the menu that allows me to in fact change some of the settings on the slider. So for a start, I can minimize the slider. So now I've got it the same form as C down here. But if I press Control Menu again, if I go to Settings, I've got a number of things I can do here. The variable is called M, being the gradient. At the moment, it's actually set on the value of 1. Again, I can change the minimum and maximum values here. But I can also change the step size that it goes up in. So at the moment, it's automatic. But if I want to go up in, say, increments of 1, I've just got to type in 1 and press OK. And so if I do that now, you can see it's going up in increments of 1. And so that's a nice little powerful visual to help us teach our students what certain parameters within an equation will actually do and alter the graph. If I move right along now, I've got another graphs page here, as you can see. And what I want to do is actually use this page to show how we can get some key features on a graphing page. So I'm just going to move that label out of the road for us. First of all, we can actually alter the maximum and minimum values. So if I just change that to 10, then I'm just going to click on the number and change it accordingly. And so I'm going to double click on this, change that to -10. I'm not want to keep making changes. I think you can possibly see the point what I'm making there. What we can do on these lines is use some of the geometry features down here, which sometimes I think we perhaps don't make a good enough use on this part of the calculator. So if I go over to points and lines, what I can do is actually plot a point on these lines. So I'm going to plot a point here on the red line, which is y equals 2x plus 1. Now, if I actually take that off, you'll notice that it just disappears. What I need to do is highlight it and either click it again or press enter so the point actually stays there. Now that I've done that, you'll notice that I've got the symbol here. That's the point on function on the calculator. That'll stay there until I actually hit escape. And the calculator, you can't do much else with the calculator until you in fact do that. Now, the number 1.1893 perhaps is not useful to us. What I can do though is actually change that value. So if I change that to 1, now the 0.13 is plotted for us. Which means, as from a point of view of a teaching tool, what we could say is say to our students, okay, I wonder how we would find the y-intercept. Hopefully one of our students will probably say, oh, maybe x should be 0. And therefore, if we show them that, they can see that that plot is pointed, that point is plotted. And we can do the same thing here if we wanted to for the x-intercept. So there's nothing stopping us plot another point. If I actually right-click in the space here, I can actually get some recent features that I've been using on the calculator, like point on. Now, right-clicking is the same as pressing Control Menu on the handheld. As you can see, I get the same menu come up. So if I go to Recent, I'm going to go to my point on function again, and if I want to put a point there, as you can see, I actually could put it right on the x-intercept there, and that's exactly what I wanted first up. So there we have it. There is the x-intercept being plotted. If I hit escape, I've turned that function off again. We've got the intersection point up here, and so there's a couple of ways of finding the intersection point. The one way that we will be most familiar with is possibly using Analyze Graph and then point of intersection. And it's just a matter of setting a lower bound, so put that dotted line to the left of the intersection, press enter or click, and then drag that across to the right, and we'll get the point of intersection. There is another way of actually finding intersection points, and I'll show that later on in the presentation. Moving right along, what we could alternatively do is actually work out the x and y intercepts using a notes page. Now, if you remember back here, if I hit the tab to get the entry line, if I hit escape again, what I'll do is I'll actually double click on one of these rules that I've graphed. That's actually rel 2 or relation 2. That's y equals 2x plus 1. Up in rel 1, I've got 2x plus y equals 12, which means what I've got coming in here are those two relations. They're plotted there. If I want to work out the y-intercept for relation 1, as you can see, I've set x equals 0, so therefore y equals 12. If I wanted to actually work out the y-intercept for relation 2, I've just got to swap the 1 for 2 and press enter, and there's the y-intercept. Underneath it, you can see I'm doing the same thing with the x-intercepts. There's the x-intercept for relation 1, which x equals 6, which would be confirmed over there. There it is. But if I wanted to do the same thing for relation 2, I can just turn around and press enter, and there it is, negative 0.5, which we had just over there. So I guess the first point I'm trying to make here, we can obviously get these key features on the graphing page here, but there's nothing stopping us using the other functions on the calculator. In this case, I'm using a notes page. Understand that when I go back over to 3.1, if I make a change here, if I make a change to rel 2, if I make this 7 and press enter, this gets automatically updated, but so does the information over here for rel 2. It gets automatically updated. And that's the nice thing about notes pages. They are live and interactive, so any changes that are made, they're automatically updated, which is a little bit different to the calculator page. Right, I'm a little bit conscious of the time. If I'm going a little bit quick, I'll apologise for that now, but don't forget that this webinar is being recorded, so in your own time, you'll be able to replay this and take perhaps things a little bit slower.
Yeah, replay and pause and go over it again.
That's exactly right, Brian.
And Craig, are you also sending us a copy of this file that to distribute?
Absolutely. So then you can go your hardest on having a play with it, and you can modify it as you will. What I've got on this next problem here is, in fact, some basic algebra stuff that algebra functions that people might find useful. And what I should actually point out to before I go any further, notice that I've got problem 1 here. This is problem 4, I should say, and this is problem 3. Problems are, as the name suggests, they are not related to one another. Problem 3 has got nothing to do with problem 4, which means if I hit problem 3, if I have a look at the variable list under problem 3, you'll notice that I've got these 3 variables here defined. But if I go over to problem 4 and have a look at the variable list, a whole different set of variables have been defined. And so the problems are not related to one another. And so there's no need to reinvent the wheel all the time.
Yeah, so the variables remain
there is a limit to how many problems you should have.
Yeah, so the variables remain connected, but within, just looking at the variables remain connected, but only within that problem.
Only within the problem, that's right, across the different pages within the same problem.
Yeah, of course we know how to add pages, like a new page within a problem. I'm just thinking it might be worth showing how we can add a new problem within the file. So
I can do that.
Yeah,
what I'll do is I'll go over to 3.2 here.
Yep.
3.2, if I press Control, I want to press Control. I hit
Control again, we'll get rid of it. Yep.
Over there.
Yep.
I've just inserted another page by mistake.
Another page? Yep.
Because I've made a mistake, I think I'll just undo that. So that's nice. If I hit Dock on the handheld, then Insert, and then Problem, I'm about to insert another problem of which I can insert some sort of page. Let's put in a calculator page for fun. So as you can see now, I've got a calculator page in problem 4. All right? Yep. And now if I hit var button over here, there's no variables that have been defined in that particular problem. I haven't used it yet.
So problem 4 is now called problem 5. Yeah.
Now I'll go to problem 5, which was problem 4. There we are. We're back to what I had before. Here I've got just solving a simple linear equation, but again, because this is a notes page, if I make the change within the maths box here, so I'll change that to 23 and press Enter, I can get the solution to the new problem. So it's just a matter of just updating or changing the equation in there and pressing Enter, and you'll get the new answer, the answer to the new question. Next, I'm actually using solve down here for simultaneous equations. And so what I'll do is I'll type in a new equation, or a new pair of equations, 3x plus 2y equals 9. And then I will change this to x take away y equals 1. Now at the moment, as you can see, I've got these two equations in terms of x and y, so I better change this to x and this to y. So comma x, comma y, press Enter, and I get the solution to my two simultaneous equations. Now further down here, what I've got is a facility where we can enter in a pair of points. So if I enter in the point 0 and 0, now I hope every time I'm pressing Enter, I'm hoping you're taking notice what actually is happening underneath. As you can see, every time I'm making a change, the calculations are getting updated. So I've got the 2 points 0, 0 and 2, 2. x1, y1, x2, y2. From there, the gradient is being calculated, which is 1, which we would know, and down underneath that, we're getting the equation of the line automatically generated. You might be interested as to how we can get the subscripts here. So I'll just quickly show that if you want to actually do your own. I'll just insert a box here. If I press Control-M to insert a maths box, Control-M. If I hit the template button, and this is the option we're using here. So I choose that, and I'm going to just use this. If I'm going to go R subscript W, you just type in the R, type in the W, press enter, there it is. So that's actually how you can format the text as such. I'll delete that now because we don't really want that there. Just a little bit further underneath what I'm just doing there, if you're doing a question where you're just given the gradient and a point, so let's say if I was given the point 1, 3, I would actually define in x1, y1, the point 1, comma 3, and then let's say the gradient of the line that we're trying to find is the gradient 5, then the equation just joining point 1 and 3 that has the gradient 5 is 5x minus 2. Now, notice that I've actually called the gradient here double M. That's because up here I've used gradient M being for the other, if you like, type of question. And so we can't have the crossover of variables or doubling of a variable, so I've called double M instead to cater for that. Moving right along, what we can also do is test solutions. So, for instance, does the point, so if I go back over here, does the point 1, 3 lie on the line, lie on the line, y equals 2x minus 1? And the answer is no. However, I might want to try and test another point. So let's say if I tried to test the point 0, I think it's going to be -1. I've actually just had a bit of a blank, but let's try that. Let's test the point 0, -1. Oh, golly, it's true. So that's how you can actually test points. And you can also test in equations the same way. That's actually picking up that that's also true. Now, what you can also do is do similar sorts of things on a graphs page where you can plot points and find the equation of a line too. So what I'll do is quickly show how to do that. If I press Menu, Geometry, Points and Lines, and Point. I'm going to plot a pair of points. There we have it. I'll hit Escape. I'll then on Menu, Geometry again, Points and Lines again. And this time I'm going to join them up with a line. So I'm going to join them up with a line. There you go. Done. Now what we'll do is I would like to know what those coordinates are. So if I click Menu, Actions, I can go to Coordinates Equations. There's that coordinate, there's that coordinate, and there's that equation of the line. I'll hit Escape to turn that off now. I'll just place that out of the road. Now what we could do, I guess, is just move the points around, and as you can see, as we move those, that is automatically updated. That's not very useful though to us really. Generally speaking, we have nice information to deal with. So let's say if that was the point, -1, 2, make this 1, 1, 5. There you have it. There's the equation joining those 2 points. So that's just another nice way of doing something that I've just already shown you, but different way of presenting the information. Sometimes the kids like to see the visual. They sort of quite literally make the connection sometimes. Right, moving right along, we can graph planes. So what I've got here is an example of some planes being, or regions being graphed. You'll notice here with this one here, x plus y equals d, I've got a slider connected. So what we could do is just teach kids what the effect of that is. So there we are.
Particularly good for the linear programming, of course.
Absolutely, Brian. Yeah. Absolutely. And if you wanted to, you could actually insert another slider if you wanted to. So what I'll do is if I double-click on this, I'm going to call this, insert the coefficient A, so I'm going to go A times by, and don't forget to go times by X, otherwise it'll read as the variable X. If I press Enter, it's going to automatically prompt, do you want this to be created as a slider? And I'm going to say, yes, I do. So I'm going to press OK, and therefore keep it ticked. If I untick that, it won't do it. So if I press OK, I have my slider for A created, which allows me to move it. So there it is. Now what I can do is now start having explore how A might affect that particular inequation as well. Now what you might notice is I've got this test point here. This is what I call the test point. So I'm going to move my test point up here. Now they're actually bold. You'll notice that they're bold. That's because I've actually connected or linked or stored that X coordinate into X1 and this Y coordinate into Y1. And then what I've done over here is I'm actually testing to see if that point is actually, within certain regions. So if you have a look at these two constraints down here, Y1 bigger than 0, X1 bigger than 0. Is that true? Well, yes, it is, because that's where it is. Both the X and the Y value is bigger than 0. If I grab that and move it down here now, though, let's actually have a see which of the constraints are now, in fact, true and which aren't. Well, now notice that this one here is true. So therefore, when you're adding the two X, the X and the Y value together, it's less than or equal to D, which can be confirmed here. But we'll also notice that, in fact, not all the constraints are, in fact, being satisfied. So maybe I need to move it elsewhere. So let's go and test this region down here instead. Aha. We've got bingo. We've got them all satisfied. Now I've just moved that around. There's nothing stopping this highlighting that and just changing that to 1 and 2 if we wanted to. And it's not going to make any difference how the information will be displayed over here. I'm a bit conscious of the time, so I'll quickly whiz through what else I've got over here. With the linear programming, I've again got a whole bunch of constraints set up here, but notice now what I've got is the points of intersection here displayed. Now, if I double-click on these, you can see these are all the constraints that I've typed in with this particular problem. But I did say before that there is another way of actually finding these points of intersection. So what I'll do is show, I've actually got the objective function here that you can actually type in an objective function and evaluate them. As you can see, that's been evaluated, so by all means have a play with that yourselves. There we have it. So we know that helps us with the problems we've got to maximise and minimise the objective function. It's just a matter of actually changing what that objective function is, and it'll get automatically updated for us. So naturally enough, we'll be getting that information from these points here. But what I was actually moving on to was, I've got another bunch of inequations here. I'm going to show you quickly how we can get these points of intersection. We press Menu. This time I'm going to go down to Geometry, Points and Lines, and Intersection Points. So if I want to work out that intersection point there, I just got to click on the blue line and the red line, and that point of intersection comes up. Now if I want this one here, if I click on the black line and the red line, it comes up. Now if I want this one, if I click on the black line and the blue line, it comes up. So it's perhaps a little bit more efficient than the other way when through Analyze if you've got a few to find. But don't forget, you've got to press Escape, and what I can then do is just move these out of the road so we can read them a bit more. So that's just a nice little feature that you might want to be aware of as well. Lastly, before I hand over to Sanjeev, graphs of the form y equals kx to the power of n. again, what we can do is use a slider to at least show what the basic shapes are. That would be a good start in terms of a demonstration tool, as a quick way of teaching what those points are, or those graphs are. And again, don't forget what we can do is plot a point on each of these and actually explain the maths, or how the shapes are actually generated. But what we've also got is the option of being able to perhaps find some rules. So what I've got here is I've got some x values, 0, 1, and 3, and I've got corresponding y values, 0, 3, and 27. Now, the question is, all right, what is the we want to be able to find the rule to that. What rule actually ends up generating those y values? So first of all, what you'll notice, I've actually got the scatter plot plotted here of the original data. Now, what I should remember, I always teach my students to, when you're actually doing a scatter plot, don't forget to zoom data and make sure all the points are there. Now, if I go across, I've now got the transformed, what I call the transformed one. So, as you can see, a nice linear straight line appears to be forming here. Now, if I go over, what I've done here now is I've got if you like, the gradient and the intercept calculated for that non-linear model. And how do I know it's a straight line? Well, as you can see, the R-squared value is 1. If in fact we made the wrong choice, so if I go back here and I thought that in fact it was a cubic model instead, so I'm going to change that to the power of 3. Then go and have a look at, first of all, the transform data, so zoom data again. That doesn't look very linear to me when you look at that. But then if you have a look at the R-squared value, no, it's not quite 1. So clearly the other model was the correct, and we've got the A and the B value that allows us to work out what the equation is. Right, I've well and truly gone over my time, Brian, so I think it's time for Sanjeev to bring it home.
Okay, you've set us up very, very well there, and I'll go so far as to say with that file, that document that the teachers are going to get, yeah, I would say that you know, they're obliged now, having seen that, they're obliged to give that to their students, I think, unless they've already written one already. I know, Craig, you're also pretty keen on putting some of those notes pages into widgets as well. So if teachers don't know what widgets are, I absolutely recommend that you find out about widgets. There is information on the website because that's very, very useful. I'm particularly looking at that linear programming exercise. I would want to have that in an exam if I was doing that module.
Yeah, I agree with you.
Yeah.
Sanjeev, this is very colourful.
Thank you.
Yeah.
Hello, everyone.
G'day, mate.
Okay. Right. Now, what you will all see is a PowerPoint, and I'll also use the calculator simultaneously. And what you see on this page is actually all done on the TI-Nspire calculator using the geometry application. So as Craig mentioned, the geometry application is very powerful, but it is not really utilized well. So that's my first screen. So I've actually, I'm talking about bearings over here. So let's look at the compass bearing over here. So I've got the bearing, and you'll see it's telling me the bearing over here. So it's at a distance of 6.4 units from the origin, and it's 42 degrees towards east from north. So when it says 6.4 N, it is measuring the angle from north towards east. And the bearing can also be then expressed in terms of from east towards north, and that would be 48 degrees from east towards north. Now, how do we do this on the calculator? All right, so I've got this page now on the calculator, and if you'll see this, I can actually move this, and it's giving me the distance. And I can actually, in the next screen, I'll show you some bits of animation. And over here, I've got this other vector. Now, at the moment, this is sitting in quadrant 3. Now, if I move it to quadrant 2, I want you to observe what's happening. So I want to read this bit over here. So at the moment, it's saying 6.9 is the distance, and it says 75 degrees west from south. Now, I want you to observe that when I move it. Now, it's measuring from north towards west, or from west towards north. So that's all done by conditional formatting. So this is all done in the geometry application. Now, these files will be available for you. So you can actually use them straight away as teaching tools. And the way it's all done, I'll probably show you in the next screen how to put some conditional formatting. But it's just fantastic, the conditional formatting. Okay, so that's how we express compass bearing. Now, if I go to the next page here, I can actually animate this. So this is a person starting from origin and moving in this direction. So you actually can animate this, and you can see it's moving towards the point. So a simple animation, how far the person is and what angle is the person moving. Now, I'll show you how the conditional formatting can be done. So that's my point. If I right-click that, which is Control Menu, you will see an option there, which is Attributes. Now, in Attributes, it allows me to change the size of the dot or the point that I was moving. So, and I can change the color as well. So I'll just make it big enough. And if I right-click that again, you will see I have an option of line color. And at the moment, I've got it at red. I can change that color. And when I'm moving my cursor to various colors, you can actually see that dot color changing. So I'll select blue there. Now, talking of conditional formatting, okay, it's at the moment sitting at 3.4 units. And I'm actually going to, you'll see it's stored as distance at the moment. Now, if I right-click that, you will see I have an option condition. And let's put a condition. And when I say distance, because I've already defined it, if distance is greater than, let's say, 4, change the color to red. Or okay, so I've changed the color to red, which is 7 and 7. So I've just line color and fill color, I've changed it to 7. So at the moment, it's disappeared. Now, if I animate, you'll see when it got past the distance of 4, it actually shows. So I can, so that's just using the condition tool. So it's pretty powerful, the condition tool. And I could go and put another condition, and I could say make that dot blue, if the distance is less than 4. So I can have 2 conditions or 3 conditions for a point. Okay, moving on to the next part over here, I've got actually a point. This is again bearing, and you can see I've got it actually as true bearing, and it shows the angle representation, and it says over there 280 degrees to north, and it says that's 4 units. If I extend it out, I'm changing the length, and if I move it, that's changing the bearing. Now, how we achieve that is again using the conditional formatting. So I put actually a format over there. If the angle is less than 100, put a 0 in front, and if it is more, then just put the actual angle there. So that's the way I've actually just represented the conditional formatting there. And just want to show you this measure part. If I go into geometry, you will see there's an option of measuring the angle, and then there is the directed angle. So I've used actually directed angle option rather than angle, because if you measure the angle, it will always go in the anti-clockwise direction, whereas directed angle, you can actually tell it how do you want to go. So if I'm going from here, let's say, let's do again measurement, directed angle. So I select a point there, and I've just gone here. So you can see here. I've just put a point there. So it's saying it's 107 with the direction. So you can actually see that. Now, because I didn't draw a line, you don't see that, but you can see the green arrow, which actually is the directed angle. So the directed angle is a very powerful use as well for bearings. So I'll head back to my PowerPoint. Now, this is actually a multi-stage movement that we are showing. So a person starts from position O, travels 7.1 units at a bearing of 53 degrees to north towards A, then turns to move towards point B, 8.6, and then the angle is 128, and so on. So the question is, how far is the person from the starting point when he is at C or any other location? So I can actually grab any of these points. If I go back to the file here, that's where we are. I can actually grab any of these points and move them. And the angle and the distance would change. So again, this is a working file straight away, and it's giving me the calculations there. So what you see, the length of GC and OG. So GC is how far, in the east direction, and GO is how far in the north direction. So we can actually measure those from here. Once again, it's done as an animation here. If you look at this, so let's move this back here. So let's look at the animation. So the person starts from position O and is moving. So it's giving us the angle there. And I can actually change the speed at which the person is moving. And now if I was to stop there, it tells me that the person is 13.7 units from the starting point and is at an angle of 109. So it's telling me the bearing straight away. 13.7 is the distance and 109 is the angle. So again, students understand this really well if you kind of do this animation. Once again, I put conditions to that. You can actually put any conditions. So that's the bit for bearings, and this is a calculation tool. So it's working out all the true bearings, theta1, theta2, and theta3. These are all the true bearings that have been calculated, and it's going to give you the distance from O to C and also the final angle. So all those measurements are there. So that's with bearings. So the next bit I'll go to is similarity. Okay. Now for similarity, I use transformation. So I'll quickly again demonstrate that, how we could do that. So going back to geometry similarity, and I'll insert a new page, and this time a geometry page. And I'm going to just draw any random shape here. So let's take a shape, probably easiest to do a triangle. So, and I've got a triangle there. If you want, you can color in the triangle. That's color, fill color. That's the color there. Okay. Now I'll go to transformations, and similarity, we are actually dilating the shape, so we can zoom it in or zoom it out. So I'm going to use the dilation option, and you'll see once I click on the dilation option, and if I go to the top of my screen, it tells me what I have to do. It says click the object and then the dilation center, or press, by what value do you want to dilate it. So I'll do that. So I'm dilating the triangle, and I want to dilate it by a factor of 3. And you'll see I have my shape which has been actually dilated by a factor of 3. And I can actually move this wherever I want, controlling that, because I can. So you'll see each of those sides. Now if I change my original shape, everything is scaled up by a factor of 3. I can actually put a slider there if I want. So I'll store the value, and let's call it, so that's going to be the dilation factor. So I'll call it df as a dilation factor. And now I can go and insert a slider if I want to control the dilation with a slider. So under actions, you will see insert a slider option, and let's call it DF. And at the moment, because it's 1, it's so you would have watched this on Craig C. Now, if I do the dilation, so at the moment the dilation is 3, the dilation is 2. So you can actually see how the shapes get dilated.
That's clever. Yeah.
Yeah. Okay, and you can actually change the value. If you want, you can put 2.2 as a dilation factor. And you can actually, once again, go and let's do this, measurement of the length. And in this case, it's actually going to give me the perimeter for the shape, which is 13.9. And if I measure the perimeter for this one, it should be 2.2 times. So let's make it easy. So the calculation is straightforward. So if I make that as 2, that value there is double of 13.9. So all the lengths get doubled. And I can do the same for the area. So measurement of area. And this would be interesting because area is square units. So the new area should be square of this value. So let's go and do that, measurement of area there. And you can see it's basically squaring the dilation factor. So you'll go 4 times 7.69. So the dilation factor is 2, so you square that 2 square times. So, and if it is volume, you will do dilation factor cube times the original area or volume, whatever it is. So that's similar shapes. And once again, the PowerPoint actually explains it all. I've got more shapes in the file. So when you have access to the file, you'll see these are the various things I've done over there. It just summarizes everything that I've done. So the scale factor, if it's the length, the new length will get scaled up by a factor of 3. If it's the perimeter, same thing. If it's the area, it will be square units. If it is volume, it would be cubic units of the square factor. So if the original volume was 12 and the scale factor is 3 on 2, so the new volume would be 12 times 1.5 cubed, which is 3 over 2. And that should give me the new volume there. Moving on to volume and surface area for cylinders, cones, and spheres. Now, I won't go through this because you'll see I've actually defined the rules over here. And you can straight away see the rules. All you do is you store this rule in your calculator. So I've defined a cylinder, the volume. So volume is pi r squared times h. Now, of course, I have to say what is r, what is h. That's the radius and that's the height. Now, I've got d is to how many decimal places do I want the answer. So I've created a slider. And I don't know if you can see the slider there, just where my cursor is. And that's the value of d. So I can change the value of d, and I'll show that on the calculator screen in a moment. So let's go to my calculator screen. Okay. All right. So that's where I should have a slider there, which is the decimal places. Now, if I change the decimal places, can you see the answer changing? Down here, it's 2 decimal places. If I click, that's giving me the answer to 3 decimal places. So I've got the formula there. That's for volume. So you will see I've used the syntax round the answer to the number of decimal places. So that's the formula, and that's rounding off the answer to a certain number of decimal places. So I've got the formula for a cylinder. I've got the formula for the cone. I've got the formula for the sphere. So in each case, it's giving me the volume and the surface area, or the total surface area if it's a cone. So everything is predefined. All you need to do is just change the radius. So let's say the cone, I change the radius to, the height to 9 units. It will change the volume and it gives me the total surface area. So it's good to predefine all these rules for volume and surface area for cylinder, any 3D shape. You can just predefine those rules. Okay.
And you can say that you're using
I'm trying to rush through everything because I'm limited for time, so I'm rushing through everything. Yeah. Yeah. Okay. So let's quickly go. So I've done that bit, and then, all right. Now this is again a 3D shape that I have done on the 3D geometry graphing and geometry page. And this just explains basically what the longitudes do and what the latitudes do. So obviously I'm not going to teach you all that, so I'm going to skip all that information. I've got over here, typical exam questions on this topic could be finding the time difference between two locations. Now if you're finding the time difference between two locations, we obviously are looking at the longitudes. And then how many hours ahead or behind a city is, in relation to the Greenwich Mean Time. Or we could just determine the distance or time between two locations. So I've just summarized that bit there. So obviously, if you're finding the time between two locations, we only need to worry about the longitude. Now, normally they would use that notation or they would write it in that. So the coordinates for a location are expressed in either of these notations. So if we are talking of Melbourne, that's telling us so we are in the southern hemisphere and in the eastern hemisphere for the longitude. So I've just got the location there. So you could see the information in that form or in that form there. And keep in mind the latitude is always listed first. Okay, so I've got a few questions here. If Singapore is located at this coordinate, so we've got the coordinates, now we're finding the time. So we really have to worry about 104 degree east for Singapore and Melbourne 145. And we want to know what's the time difference. So that's on the calculator. So we take the Melbourne longitude and Singapore longitude, we take the difference and times it by 1/15. And 1/15 because if I go back to my previous screen, which explains here, in 1 hour the Earth rotates by 15 degrees, and that's how I got 1/15. Or I could use this, every 4 minutes the Earth is rotating by 1 degree. So the reason I multiply by 1/15 is that. So that's where we are. And if I do Control Enter, it gives me 2.733. Now, you would realize students, obviously, they won't get marked too well if they write 2.733. So we want to convert that into hours, minutes, and seconds. And to do that, I can actually use the DMS option, which is degrees, minutes, and seconds. If I do degrees, minutes, and seconds of my answer, it gives me 2 hours. So degrees should be read as hours. So it's 2 hours, 43 minutes, and 60 seconds approximated. Now, obviously, we work in half-an-hour time zones, so 2:43 is rounded up to 3 hours. So the time difference between Melbourne and Singapore is 3 hours. So that's done on the calculator. So again, it shows how to use the DMS option. It's the calculator screen capture is there. There's another question there where we are trying to find, the time difference from Melbourne to New Delhi, Auckland, and New York, and how it can be done on the calculator is demonstrated there. So the question is, what is the current, if the time in Melbourne is 12:30 in the afternoon, so if I go back, so it says the current time in Melbourne is 12:30 on 22nd of August, that's today, determine the time and date in each of these locations. So I've rounded off the longitude values. So 144.96 is rounded off to 145 and so on. So those are the longitude values at various locations. And this is what I've done. So the current time minus, whatever is the time difference, we're doing that. So it tells me the time in New Delhi should be 7:58 when it is 12:30 in the afternoon over here. So 7:58 morning. So obviously that needs to be rounded to 8 a.m. So time in Delhi would be 8 a.m. Likewise, time in New York, actually I have to go a day backwards. So it's 22:54 will be rounded to 23 hours, which is 11 p.m. of the 21st. So the next screen will demonstrate that. And Auckland is ahead of us, and that's why it's plus over there. And when it's 12:30 in Melbourne, it will be 2:30 in Auckland. So that's how. So you can see the calculator syntax. So that's all from the calculator. The screen captures. So once again, another way of doing it. So if you try this on your calculator, you'll see it works well. And you'll see for Melbourne, actually, I've got -14 hours. So that means I'm going backwards. And likewise for New Delhi, I'm going backwards. So they are behind. So the value itself will tell you whether you need to go backwards or forward. All right, so that just demonstrates how to use the round feature. And okay.
Yeah.
These screens are self-explanatory. I'll skip this, and I'll go to the last bit. And you will all have access to this file, and I've got this file over here. I'll probably go into the calculator mode. So here, now this is actually a predefined program for finding the, right, so it's called solve triangle, and I just want to demonstrate what it will do. So I can insert a new calculator page, and if I go into my variables, I've got all the variables there, but the one I'm using is the solve triangle. And it says enter 0 if the side length or angle is unknown, else enter the known value. So I need to enter 3 of the values. So let's say side A is 4 units. Click enter. Angle A, I'll leave it at 35, or you can change that. Let's change it to 45. And side B is 6. So I have supplied 3 bits of information, and that should be sufficient. And I'll put that as 0, and 0, and 0. Domain. So I probably don't get a triangle. So if I go and edit that, I would have made. But if I put the correct values, so let's try to run that again. Yeah. So insert.
Yeah, so it's possible to put in a test there to say these won't make a triangle. Depends how much you would want to put in the code. Yeah, we're just on time there, Sanjeev.
Yeah. So just the last one. So let's do 7, and let's do 60. Okay, and I'll put that as 0, and angle is maybe 55. So I've supplied 3 bits of information. Hopefully that should work. Yes. And you'll see it says I have a triangle with these specifications. It gives you side A is 7, angle A is 60, side B is 6.6, angle B is 55, side C is this, and angle C is this, and the area. So it gives you everything. And it takes actually the care of the anomalous, that sign rule situation. So I'll stop here. And I actually have more material which you can actually access through the file. So Brian will pass on the files to you, and you should be free to straight away start using them in your class. Thank you, everyone.
Terrific. Thank you, Sanjeev. As always, we just have more material than we have time for. But the good thing is, as Sanjeev mentioned, that you do get a copy of this mailed out. So that will come to an email address near you. Now's your opportunity to type in any final questions to both Sanjeev and Craig, who are both still online. And of course, you can also use the chat box to type in your gratitude. I know I'm happy with what they've shared with us. So thank you once again, Craig.
Pleasure.
And thank you again, Sanjeev.
My pleasure. Thank you. Yep.
Now, the good news is, if you've enjoyed this, I know we're over time, but I'm just going to jump in to show something else. If you've enjoyed this evening's webinar, we're putting this team back together again. And if you look at the webinar on the 5th of September, a couple of weeks' time, I think we're again a Wednesday evening, yep. We will have both Sanjeev and Craig presenting again for further mathematics for exam preparation or exam readiness. And I tend to think what we've got tonight was actually a lot along those lines. Can I just also point out that both these presenters were also instrumental in helping build a resource for students last year, and this is exactly targeted for exam preparation. So as you see on your screen now, VCE student exam preparation for further maths. Can I just quickly, as I said, I'm aware we're over time, but I could just quickly show that to get to that, if you go to the Texas Instruments website, I'm just waiting for this to jump into this. If you go to the Texas Instruments website, and where we normally pull down the tab for teachers, for teacher resources, click on the one that says Students and Student Resources. I can see that the computer is taking a while to catch up there. Under Student Resources, Student Resource Centre, the tab Prepare for Exams, and select your state, and you see here video applications for further maths, and we get the range of topics down here. So I think a terrific, these are just short little videos just to help students. It's not going to teach them a topic. They should know the topics by now, but it's a review as they lead into their exams. I think an invaluable resource. You saw also that it's there for maths methods and special maths as well. So thank you again to both our presenters. When I close the event, you'll be taken to a page where we invite your feedback. Please provide that to us so that we can modify these and keep providing them as best suit your needs. Remember, you will be getting the files from tonight's webinar in an email along with a certificate for your attendance. I'm always hopeful that more teachers might be able to join us for a guest spot in our webinars. You can do that. Please email me if you're interested. And a reminder that you can watch this all again in the on-demand webinars or also on our YouTube channel. So finally, thank you to our participants, thank you especially to our presenters, and good evening to all.
Thank you, Brian, and good night.
Thanks,
good night, everybody.
Good night.